welcome Professor Boiten tonight. He's already shared his screen, so over to you, Prof.
Okay, thanks very much for the introduction, Kay, and thanks very much BCS Leicester branch, of which I'm also part, for inviting me to give this talk. I think it's an important topic, and it is my personal perspective on recent developments in AI, and I'm happy to invite discussion about it. I won't be able to look at the chat all the time while I'm talking, but we can certainly catch up later. Let's see. Yeah, I don't currently see the chat, and it probably doesn't work that well that way. But we'll come to questions. I love questions. I love to be proved wrong about all this. So the talk is called Nearly 60 Years of Software Engineering and Formal Methods versus AI Safety. I first spoke about this topic last summer at a national event training event on AI safety, and part of the abstract of that was talking about systems are so complex that their behavior is not fully understood. Okay, that's so far slightly worrisome, but that their behavior is not fully understood by their designers. Well, this irks me as a software engineering trained person. That can't be right. Is that really the world we're in? Well, let's look at it a bit more closely. So I spoke about AI ethics for the first and last time around 2018, and at that point I was a little bit disappointed with what was going on there. I'd heard of AI before. I am nearly as old as the 60 years that appear in the title. And when I was an undergraduate in 1985 or 86, I took an optional module on AI. So this beast called AI has been around for a little bit. But around 2018, I was getting the feeling that there were two things going on at the same time. Two bits were crossing the responsibility horizon, if you like. So programmers used to be responsible for what their programs did, but with the development of machine learning, it became a bit unclear who was still responsible for it. Yeah, it's just the algorithm, or it just does that, and it's been trained, so it must be right. And on the other hand, the data that goes into this in the context of the surveillance society, over my right shoulder, I've got Shoshana Zuboff's book, The Age of Surveillance Capitalism, standing there just for the fun of it. We moved from data on which we did data protection to big data on which, well, do we still care where it comes from and how it's being treated? So I was a bit worried about that. Fortunately, we had sort of responsible AI developments, and people. I stopped giving talks about this at that point because there were so many people rushing ahead, having good ideas about responsible AI. And there was even a movement, a thing called explainable AI, which sounded very promising. So AI systems that will actually be able to explain what they're doing. Unfortunately, things have got worse since then. So let me put up a picture of a man who is certainly very famous in Germany. I'm from the Netherlands, by the way, but I have a personal link with this man, which will pop up soon. So this is Fritz Bauer, and he was a professor at the Technical University in Munich. He died in 2015, and he came up with the text underneath. The establishment and the use of sound engineering principles to economically obtain software that is reliable and works on real machines efficiently. It's a definition of something. Anybody guess what it's a definition of? Well, don't unmute yourself too quickly, but it's one of the first definitions of software engineering. Right? Sound engineering, economically obtained software, reliable, works on real machines. And he was actually the organizer of one of the first events on software engineering, organized by the NATO Science Committee in Garmisch-Partenkirchen in south of Germany. in 1968. This is one of the places where they talked about the software crisis. And the proceedings of this were gathered by Brian Randall and Peter Nauer. Brian Randall is still an emeritus professor at Newcastle. So this is an exciting book. This is a photo from the internet. I've got a copy of it, inherited from a retired professor at my previous institution. And I would say, from my perspective, and you have to take into account, I started my computer science degree in 1983. From my perspective, the Garmisch Conference was very much at the heart of what I would see as essential progress in computer science. So a lot of things around programming language design started at or near this event. The IFIP Working Group 2.1, which defined Algol 68, and I think before it Algol 60 as well, and IFIP Working Group 2.3, which split off from it with Weert and Dijkstra and other big names in it. I think the field of formal methods had a strong link to this as well. So people who were there were Eerke Dijkstra, David Gries, and also Frits Bauer. And this is also where software engineering became prominent. Some Wikipedia pages will say that the term software engineering was coined by Frits Bauer or at this meeting, but there are also, of course, probably more reliable reports that the term came from Margaret Hamilton at NASA. I hope I get the name right here. Yeah. But around this time anyway. And what all these areas have in common, programming languages, formal methods, and software engineering, is that you end up working with abstractions and notations to express those abstractions in. So using mathematical logic in one way or another, having programming languages that are higher level or maybe pseudocode, and some notion of how all these things relate to actual programs, either at the level of a compiler or when you talk about formal methods in the level of mathematical understanding of what the program really should be doing. So closely tied to its semantics. And the other thing that sort of began to come up at this point was that you split things up a little bit. You separate concerns because that's the only way that you can manage scale. Yeah, this in some sense was a point where people felt that we couldn't understand. The programs definitely weren't toy programs anymore. They were getting too large to understand without additional structure to it. So software engineering came out, and where formal compiler construction already gives us programs as mathematical objects, software engineering also tries to define processes that get us to a program, right? And I am talking to the BCS today, and the BCS, the ACM, IET, and many other organizations have also sort of stuck onto the idea of software engineering and have come up with professional codes for how to do software engineering, software development in a responsible way. And yeah, organizations around that. And what's software engineering, in my view, is characterized by is that we do things in an organized way. So there are clearly defined processes. And typically there are clearly defined phases. And every phase produces an artifact that at some level is comprehensible to the people who have to work with it, right? And in each phase, there are sort of structured approaches to how you can work your way through that phase. So for requirements engineering, for design, for implementation, for testing. And you need to deal with the scale, so you end up with systems built from components one way or another. Even in Algol 68 and Pascal, there were already procedures, even if they didn't have classes or abstract data types or anything like that. Although of course Simula from the same era and same family did have classes already. So these ideas were very much coming on also 60 years ago. So you have components in order to separate your concern, in order to be able to talk about abstract things like sets and stacks and whatever else, and to be able to split your program into modules, into separate files at some stage, and allowing you to reuse these modules or to reuse libraries or APIs with an idea that you can actually understand all these things in separation, in isolation. And the end goal of this is that by separating your concerns, you will be able to produce reliable outcomes with a high degree of confidence. All right, so talking a bit about myself now. As I said, I started my undergraduate degree in 1983, and I feel very much a product of all that stuff that came out of Garmisch and things around that. So I did my undergraduate degree at the University of Twente in the Netherlands. The degree program was called not computer science but Informatica. It's a bit like informatics, but probably it was as technical as computer science is and was in the UK. My first programming language was Algol 68. I was exposed to functional programming languages at various points in my degree, which also suffer from some of these idealistic ideas about abstraction and all that. And I specialized in my undergraduate thesis in a topic related to compiler construction and programming environments. Next, I did my PhD at the University of at Radboud University in Nijmegen with Professor Helmut Partsch, who unfortunately died last year. And Helmut Partsch was a PhD student of Fritz Bauer that I showed earlier. So the Fritz Bauer that I showed you a few slides back is my academic grandfather, if you like, right? And yeah, David Gries was also one of his PhD students, so he's my academic uncle. Other famous uncles include Martin Wiersing, Manfred Breu, Peter Pepper, and there are quite a few spread across Germany. And many of my academic cousins are professors, many of them in Germany, and many of them also in the US, because David Gries also supervised an enormous number of PhD students. My PhD was on transformational programming, which is the idea that you can stepwise, using correctness preserving transformations, turn a specification into a program. And since then I continued with research in formal methods. I wrote what possibly could have been the last books on two topics here. So the last book ever published on Z was Refinement in Z and Object Z that John Derrick and I published, second edition, in 2014. And the last book that I've seen published on refinement is the book that we did in 2018, top of my head. Since 2008, I've been more concerned with cybersecurity than with formal methods, but I keep my feet in that topic as well. So that's where I'm coming from. I'm just old, right? If you're sitting there thinking, this is an old guy talking about modern stuff, and of course he doesn't like it. Well, if that's the way that you want to look at it, that's fine with me. But hopefully, I've still got something interesting to say. So formal methods is the area that I've been working in for the first 20-odd years of my career, and yeah, let me talk a little bit about what it has and hasn't done, because it's quite easy you can encounter people who think formal methods are not much good, right? The first ever interview I did for a job as professor, probably 10 years too early for that. I encountered probably the most famous software engineering person in the entire country, and Ian Somerville was on the panel and asked me questions. What has formal methods really done for us? And I had some answers, but I also have my doubts here, right? So formal methods probably starts with a paper by Floyd in '67 called Assigning Meanings to Programs, and Tony Hoare turned it into an axiomatic basis for computer programming in '69. So yes, formal methods is 56 years old, that sort of time. Now, I would like to distinguish between what you might call strong formal methods and weak formal methods. And the strong formal methods proposition is that you start with a completely formal specification of everything that you ever wanted your program to do, and then you get from that to a running program by steps that are all fully mathematical and logical. Right, and by the correctness of your steps and by the correctness of your initial specification, which being a bit of mathematics is easily comprehensible, at least to mathematicians, then you know that your program is correct. Yeah, I see people in the audience laughing, and I think it's a nice parable. But I think realistically. And it's voice testing. Let me just say this quote from Dijkstra comes back later. Dijkstra said he's the I think the only Dutch Turing Award winner, but certainly the most famous one of them. He said that testing can be used to show the presence of bugs, but never their absence. Right? I think strong formal methods clearly has failed, because the systems that are out there are just out of scale for the sort of techniques, right? They are more complex, they are more heterogeneous, and actually the number of different sorting algorithms that you find in them is relatively limited. They are really short on the sort of algorithms that you can derive. I mean, the Burstall and Darlington paper where it's just John Darlington. The Darlington paper where he derives functional versions of all different sorting algorithms from the simple specification that the output is the same bag as the input, and but the output is sorted, is beautiful, but it is of limited practical relevance. But on the other hand, research into formal methods, I believe, has also led to a lot of mature techniques in areas where we do want that extra bit of confidence in safety critical systems. I think ideas in static analysis, runtime verification, test generation, and model checking all have their place. All are used in practice in limited application areas where it matters a lot more, where the investment is worth it. Right? I think that's probably the other argument against against formal methods. That while maybe where you could do it in principle, is the degree of confidence that you derive from it worth the investment? And in many cases, the answer is possibly not. But in those limited areas, I think thinking about programs in a formal way and thinking about properties that you can prove of programs, properties that you want your program to satisfy, and then using tools that actually allow you to do that has achieved some level of success. But the other thing to look at is that the functional behavior, the input-output behavior of a program is not the only thing about it that matters. Right? What resources it consumes matters. How secure it is matters, and most of those things are, don't. Well, Formal methods and formal techniques have delivered something in achieving those properties, but not nearly enough as on functional input-output behavior. And if you look at reactive systems or process algebras and things like that, then broadly speaking, the techniques are much better for proving safety, proving that bad things don't happen, than on proving progress-related properties or fairness or things like that. Things that are concerned with that the right thing eventually happens. And I think that this, I'm saying this also to flash forward to what I think is partial explanation of this, which hits AI systems much worse, because I haven't said much about AI at all yet, have I? Okay, so getting towards that, I want to talk about emergent behavior. Okay, emergent behavior, for today, I'm defining that as behavior of a larger system that you can't easily connect to either the parts of the system or to how those parts have been put together. Right? So the system does something, but you can't really deduce the something from the components. It emerges in some way. By definition, of course, this is at odds with the idea of compositionality in software engineering, where compositionality really is the idea that you can look at components, and if you build something from components, you don't have to look at the components themselves anymore, but you work with some abstract version of it, and you don't care which concrete implementation of that functionality you use. And that allows you to analyze and test and whatever systems separately. So that's almost the opposite of emergent behavior. Now, in formal methods, people have done some experiments with emergent behavior. Graham Smith and others did some work at one point. People in York did some work at one point. A typical example was Conway's Game of Life, where you have a couple of cells that get activated and you get things moving off your screen. And people have been looking at systems of systems as well. But in my mind, that hasn't been tremendously successful. And that actually, I think there's an overlap between the areas where I just said that formal methods hasn't achieved much, or is finding things a lot harder, with emergent behavior. So side channel attacks, for example, is something that formal methods haven't been able to derive in terms of security, and resource usage is a similar sort of thing. So the end conclusion, if we're talking about emergent behavior, is that there's nothing that we can do to support it in development, because compositionality doesn't help, and the best we can do is verify afterwards whether it looks like something that we were looking for, but there's nothing much to guide us there on the way. So modern AI. Modern AI is all about emergent behavior, right? So what am I talking about when I talk about modern AI? And I'm talking about particular brands of modern AI, including nearly all generative AI, nearly everything that DeepMind does, everything based on neural networks. So you've got a fixed collection of neurons. Neurons are connected in a fixed way. And the output of each neuron is computed on the basis of its inputs, and there's some weights attached to each input, and there's an activation function that tells you how those weighted inputs translate into an output. And you've got a fixed connection structure between them. There might be a number of layers. There might be an output layer, input layer, and output layer. There may be hidden layers. There may be recurrence. There may be things called convolution, which means that certain areas are closely connected, but other area, neurons are connected to neurons nearby, but not to neurons further away, roughly speaking. And then there's the modern things that go into ChatGPT and the like, transformers and attention, which are all particular patterns of loops and recurrence in there. Okay, so you've got this whole network of neurons connected in a sort of fixed way, and there's weights living on the on every input, and then it does nothing. Well, it does something, but it only does something really after you've trained it, or after you've changed the weight, which are also known as the parameters, on the basis of training data. And the state of the art is that we're looking at neural networks which have billions of these nodes, or billions of parameters at least. And typically each of these weights is about 4 bytes. This gives on the order of 2 to the trillion different configurations, or 2 to the many trillions different configurations, or in which a neural network like that can compute a function between input and output. So mathematically, this is all entirely precise at the structural level, but anything that it does in the way of functionality is emergent functionality. Okay, how am I doing? Right. So yes, as I said, this slightly dismissive definition of current AI is purely for discussion's sake, but it covers an awful lot, right? So it includes large language models, just about everything in the way of generative AI. It includes DeepMind playing Go and other games, other deep learning networks, generative adversarial networks, convolution for image processing, all of those, right? So all these models do nothing meaningful until you've actually trained them. And before that and after that, there's only structure with meaningless outputs. To train these systems, these days we use, unless they're called DeepSeek and they're from China, of course, but we use a massive computational effort, right? They get trained. Typical systems, typical large language models get trained on anything and everything that people could find for free on the internet, roughly speaking, and that takes millions of kilowatt hours or millions of dollars for a large system. And once that's been done, there might be a little bit of an attempt to adapt the systems to what humans like better by doing reinforcement learning with human feedback, or putting guardrails and things like that. So yeah, a lot of machine training, a lot of typically self-supervised training, not supervised, but self-supervised or unsupervised. And then we have a system with system of weights, and we adapt it a little bit with human feedback. Now these systems are, in a way, they are stochastic, or many of them are stochastic. They're not deterministic. They don't always give the same answer, or they're embedded in a context which makes sure that they don't always give the same answer, because what they actually compute is some sort of distribution, and they give outputs that match that distribution. And yeah, this is what I would call current AI systems. That these are the properties of them. And I would say the most extreme form of current AI is probably what I would call LLM functionalism, which is the idea that if you've got ChatGPT and you phrase your question to ChatGPT, that anything it answers is sort of an answer to that question to any level, any degree of accuracy, because ChatGPT happens to know this, or it happens not to know this, but taking that seriously in any sort of way. Okay. Now, when I talk about AI and software, I am talking about AI as software, right? So I am talking about AI systems as a standalone thing. I am particularly not talking about co-pilots for code and things like that, things that generate that generate code, because if we have an AI system that generates code, then we can manage that code again, in the same way that we manage code that's written by a software engineering apprentice. And yeah, you decide how good the sorcerer's apprentice is in this respect. But I am talking about using AI as the program, not using AI to create a program. Modern generative current AI or intuition example-based AI. AI Safety Dance is a nice website to see a playful explanation of this, right? The old version of the previous waves of AI were about symbolic AI, were about creating explicit knowledge models of the world, creating sets of rules in way the world works. And that's not what current AI systems do. They don't have explicit views of the world. So yeah, my dad was a vicar. So my dad is still a retired vicar. So I'm going slightly like Luther here. And I'll give you my set of in bold. I'll give you my set of statements on why AI has ruined everything in terms of software engineering, from a software engineering perspective, right? So the first statement here is that current AI systems they do not just avoid the explicit creation of models. Their main areas of application so far are where humans don't even know how to create explicit models, right? I could call it the science of I know it when I see it. I don't know whether you know that reference, but this is an American judge who was characterizing porn in 1964. He couldn't give a definition of it, but he knew it when he saw it. And many of image recognition was, of course, an important inspiration area for many of the current AI systems, recognizing cats and dogs and things like that. And if you give the system enough labeled examples, it will eventually know. But unfortunately, if there are no explicit models of knowledge at any step, then also no models exist of what this system actually does, right? In software engineering, you like to think about stepwise development, where at every step you've got something that's slightly less abstract and slightly more specific about what you're trying to, a version of what you're trying to build, model-based engineering and all those sort of funny things. But in this case, there are no models. There are no more abstract versions around of the system as it eventually runs. So there's no ways that there are no phases in development really. So that's one downer there. Okay, second downer, and I think this is more as an aside, that most people who build AI systems these days do not reveal where they got training data, and they could be more honest about it, but statements they make would remain essentially unverifiable. I mean, there are techniques that would allow us to have some confidence that particular data is part of the training set, but full information about training sets is unverifiable. Okay, now, given that there are no explicit models of knowledge, we're also in the unfortunate situation that almost by definition, the current AI systems are unable to explain their reasoning, if there is any, because they don't actually reason. And in the happy world of explainable AI, we were hoping that somebody could explain why the AI system had taken a particular decision. and maybe feeding a human in the loop somehow. But unfortunately, in these current AI systems, as I call them, the human cannot actually learn from the system other than by following its input data to conclusion from the output data, output conclusion from the input data by themselves, right? In a world where, in a context where you actually where you create intermediate models of the world, such a human in the loop can discover concepts that occur in that model of the world, and maybe there are useful concepts that would allow the humans to improve their general knowledge of the problem area, right? So if the image recognition system for cancer detection spots makes the decision that this is a case of cancer and the doctor hadn't thought so, then the doctor is sort of a little bit lost as why that might be the case, and is a little bit lost as to how the doctor might do better next time. So yeah, that's a bit tough. On top of that, because these systems often are stochastic, it might not even take the same decision next time. That hits in a number of ways. Okay, so all behavior is in these systems is emergent. So first thing is that formal methods cannot support the development of these sort of systems, because formal methods have proven, well, yeah, you may think this is not a big loss, but just wait for it. Formal methods do badly with emergent properties, full stop. But it gets worse. These systems have no compositionality properties, which means, and this is probably the biggest, well, this one of the two biggest problems. You can't do anything but analyze the system as a whole. There are no meaningful parts. There are no meaningful components. There are no meaningful ways in which the components can be analyzed separately and implemented separately, implemented in parallel by teams, reused by others with confidence because you've already debugged the components. None of that exists. And certainly if you're a proponent of libraries and open source software and things like that, that surely is one of the big advantages of more traditional software engineering methods. Right, so we can't do partwise. I already said we can't do stepwise development. We also can't do partwise development. Okay, so let's talk about Dijkstra and testing for a bit longer. So a paraphrase of Dijkstra, I guess, is that the strongest guarantee that you can establish by testing is that you find at least as many bugs when you test as when you don't do testing. Right, so yeah, stochastic systems have a small problem with testing. Well, maybe not. Well, yeah, that's only a small problem, really. So if you test a stochastic system and you get the right output, you get the output that you wanted to get. That doesn't tell you that the system will always do that. It doesn't even tell you that the system will do this often enough, or most of the time, or whatever sort of knowledge you want on that, right? So yeah, maybe you'd have to repeat testing, but you already can't test enough. All current serious software has this property, but certainly current AI systems have an input and state space that's too large for exhaustive testing, right? The state space, I already said, was on the order of 2 to the trillions different potential configurations. You clearly can't test it for all possible versions of that. And even if you have a fixed set of weights, then well, the number of inputs that you get, etc., is also the size of your input layer, I guess. So it gets a bit big. So you can't do exhaustive testing. And as I said, that's a bit duh. Most realistic system, you can't test all possible inputs, right? But I had to say it because in all other systems we have sort of ways to go around this. So in testing in software engineering, we think about testing of components, testing of methods within components, or if we think about large monolithic bits of code, we think about coverage. Is every statement covered? Is every branch covered? None of that works because there are no components, and also in principle, the way neural networks work, every neuron is involved in every computation, right? So there is everything is covered by definition, but there's no other meaningful notion of coverage. Maybe someone can invent one. This is one where there's maybe a gap, maybe some potential. Now, testing and bug fixing. If we've tested a system and we found a bug, what we do in software engineering, at least in theory, is we fix the bug and then we run all the tests that we ran before. It's called regression testing, and we check whether they all pass again. Yeah, this is the way for us to guarantee that the bug we've just fixed, the fix we've just introduced, doesn't actually break something else somewhere. The only way to change current AI system, neural networks-based systems, is to retrain it to make sure that the bad behavior disappears. But that retraining is in no way monotonic, so you can't be sure that you don't introduce wrong behavior somewhere else by doing so. And you also have no way of systematically discovering trying to find out whether you haven't broken something else. So bug fixing, testing and bug fixing, in principle, leads nowhere on these sort of systems. Anyway, yes, I have a suspicion that the current AI systems like this, people talk about hallucinations. I would call them fault. They could be related to bad training data, and the more of the training data is regurgitating using the inputs of the outputs of other AI systems, the larger the chance. But more seriously, I think AI systems like this will typically always give an answer, even when they've not seen many examples of something. So when they're in a sparse zone of their input domain, and they have no sense of confidence, so they always give a confidence. They will often give a confident wrong answer. I have this one. I don't know for sure. I don't know for sure that the error behavior of current AI systems itself is emergent, but I've also not seen counterexample. So this is a worry. There are errors, and we don't understand when the errors. Well, we know why these errors arise, but we don't spot them. We can't spot them as systematically as I'd like to. Okay, and I mentioned human feedback and all that, and I would like to throw an argument of scale at that. So I don't think human effort will ever fix these faults, because there's just an argument of scale. The amount of the amount of machine training that's gone into these systems is astronomically larger than the amount of human effort that's gone into it, and an astronomically large system still has a near astronomical number of faults in it, and you need an astronomical amount of human time to get them all out. And as I said, getting them out is also problematic. Okay, so getting towards the end of my statement and getting towards the end of talking about this for 45 minutes now, I feel that because of all this, we can't actually use current AI systems for critical applications because they get things wrong. We have no confidence when they do get things wrong, and we can't fix it. So, in summary, what's happened since Garmisch 1968? We've learned to do program development by steps and by parts. Current AI systems do not allow for either of those, and not for any meaningful post hoc verification either. And as speaking to the BCS and writing in their magazine recently as well on the same topic, I believe that in many contexts, the use of neural network-based AI systems actually violates the responsibility principle of software engineering that is embedded in professional codes of organizations like the BCS. So, after all this doom, is there a light on the horizon? Well, yes, I am a human. Humans make different types of mistakes than AI systems. I am not a neural network, but I do make mistakes. So I may well be wrong, and I hope to be proved wrong on any and all of what I've said just now. But I am not convinced that compositionality and verifiability can get tagged on to these systems. Doing explainability through counterfactuals, or having systems that actually have some level of confidence, explicit reported, would be quite a step forward. There may be new techniques. I don't think they will build on these techniques, but maybe I'm wrong there. Of course, that doesn't mean AI systems being this unreliable doesn't mean that you can't use them. As long as you know that you're using a system, if you build some context around it that mitigates for the fact that the AI system itself is unreliable, or if you don't have high expectations of correctness to start with, right? An AI system to predict the weather is not significantly worse or different from statistics-based systems that we've used to predict the weather previously, if AI and statistics are already two different things in the first place, because we know it's only a prediction, right? But so that's in that sense, weather prediction is not a serious application in the same sense, because it's not an application where we want some confidence that the system actually does the right thing. Maybe there's some scope for some sort of compositionality. I've seen people try to use category theory for neural networks already. That may well be doomed. My ex-colleague Erik Meyer was talking about neural network higher level programming language. Well, good luck, and I hope it works something. He's very bright. But broadly speaking, I would say, if we talk about AI safety, it just means not using current AI systems in critical contexts. And I will stop sharing and I will start looking at the chat. Okay. Okay, there are some questions appearing. Okay.
Yeah. So do you want me to read them for you, or how do you want me to go about it?
Okay, well, it's okay. I can see them now. It's fine.
Okay.
Right. So thanks, Paul, for being older than me. Okay. Zhangjiang Lu. Given the growing role of structured interactions in AI, such as retrieval, augmented generation, federated learning, decentralized multi-agent system, would it not be premature to dismiss formal methods? Communication protocols and protocols. Yeah, I think that's a nice point. If you have agents, you will have communication protocols, but that will. I doubt if the agents themselves are systems, current AI systems, if you like, then you can't build on top of sand. So you still need to have some level of confidence that the agents themselves do what they do, and then the layer of communication on top of that you can formalize and verify efficiently. So and yes, retrieval or augmented generation systems. Yes, that there's hopefully some prospect there. In context of using AI for program verification, AI systems that come up with potential invariants and things like that, and then stand that off to a theorem prover. There are some corners in which formal methods like technique would be useful. Yeah. And a question from Kay: given the rapid advancement in AI large language models like GPT, do you consider them a potential threat to the field of software engineering? The answer is no. I don't believe the large advancements go very far. I don't believe the scaling laws that people are talking about are actually applying. I think we're seeing a small increase in plausibility against a large increase in training efforts. So I'm not convinced that this LLM path is leading to AGI or even leading itself to further improvement. That there is the source of where should the source of improvement come from? From more data, but that everything's been swallowed up already. So touching on could this lead to reduced demand for human software engineers in the future? I'm not sure, because I'm also hearing sounds that actually fixing wrong AI generated software is as challenging or more challenging than creating it from scratch in some cases. So yeah, writing routine software using co-pilots and tools like that, I can believe in, but where the effort's really needed, where it gets complex, I'm not sure that it will be that much help. Well, let's watch that space. Okay, and question from Arcos, a political question. Well, I'm fond of those. What do I make of the UK's AI Safety Summit? And the more recent blueprint to turbocharge. Is it intractable and a waste of public money? I have lots of opinions on that. The latest development, of course, is that the UK government has ditched AI safety. Only this week, they've rebranded their AI Safety Institute to being an AI Security Institute, looking at not so much the safe use of AI, but at AI in security-related issues like using AI for cyber attacks and also using AI for detecting nasty material on the internet. And that's an interesting development. I think AI safety, as it was, you have to know what AI safety really meant. Okay, to some people it meant that AGI won't happen, or it won't kill off all humans. That's an extreme view that's actually fairly popular in some pretty powerful corners. The more modest version of AI safety is that you define benchmarks of things that AI systems really shouldn't be saying, and if the system passes 55% of the benchmark, that's already a good score. But the benchmarks are defined by the people who work in this area themselves, so they're a little bit dubious like that. Benchmarks are things like, can you get this large language model to give you the instructions for building a bomb, or dubious stuff like that. So that's one form of safety. That's the form of safety that the AI safety thingy was concentrated on. What I would have liked AI safety to concentrate on, and which it hasn't, is this decision on which contexts it's actually safe to use an AI system to influence or make decisions in a close involvement with civil society, and with analysis that comes closer to a data protection impact assessment than it comes to a benchmark test. And that's a missed trick, a missed priority of the previous and the current UK government. Question from Paul: training data can introduce bias. Yes, but training data is only the story about bias is more complex than that. But yes, definitely bias. David, about Q developer, I don't know that one yet. I'll have to think about that. Thank you for asking the question. I have to look in that. And Akos also asks about privacy. Well, that's also a big one, because we don't, generally speaking, we don't know what data has gone into AI systems, what data will be revealed by AI systems. And it's like language models particularly, we know that potentially anything that you give to ChatGPT could be used for retraining. They may make promises that they don't, but again, those promises are non-verifiable. Yeah, lots more to say there. Okay, I think I've come to the end of the questions in the chat, but I'm happy to answer any further questions. Maybe someone wants to unmute and ask a question in person at this point.
Yes. Thank you very much, Prof. I think the floor is open for us to interact. So I think so if you are not willing to put your questions in the chat, you can open your camera, and let's have interaction and discussion. So although my question has already been dealt with, so thank you very much, Prof. So the floor is open for us, please.
Eerke, can I ask you a question? I found that very interesting.
Thank you.
I've got a feeling that whether we like it or not, AI is kind of going to be done to us. You know, there's commercial interests and there's political interests, and the commercial folk have told the politicians that it will solve all these problems for the NHS and the military and the medical industrial complex, and the military industrial complex sees a way to making money for it. And in that kind of context, isn't it the role of IT professionals maybe to see how this can be mitigated? And do you have any ideas on that? It's going to happen anyway. So I guess the challenge for IT professionals is, how do we contain this and mitigate it in the face of, you know, a lot of heavy external pressures that are pushing it forwards? It's philosophical, but it's something I thought was interesting.
No, I think you're fully right, Colin. I think we will see AI being introduced in lots of contexts, and it will work imperfectly. And if we're lucky, we will notice it when it's working imperfectly, right? I'm from the Netherlands. What not many people know, and I've told this to a Labour politician not too long ago, is that in the Netherlands a full government has actually fallen because somewhere in the benefit system they used an unfair algorithm, AI technique, whatever, to find out, to discover people who had, well, who were, according to some measure of risk, were at higher risk of having committed benefit fraud, or they biased where they looked more closely through an unfair algorithm, and people lost years of child benefits and whatever else through that, and that was quite painful. So yeah, and they found out eventually, right? We are going to do, as a discipline, we are going to have to do our very best to mitigate this, to find, I guess it is to work on techniques that can monitor AI, right? To make sure that wherever an AI system comes up with a prediction or a guess, that we've got the strongest machinery available around it to verify those guesses, and I think retrieval augmented generative AI is one example of that. That you don't actually just reproduce something that the system somewhere saw on the internet, but you also go back to finding where it found it and making it verifiable that way. Right. Of course, I work at a university, and we deal with the question of do our students use ChatGPT? Yeah, and for students doing plagiarism of the old-fashioned kind, most universities use a system called Turnitin, and Turnitin gives a score that indicates some sort of likelihood of whether the student has plagiarized from some source that the Turnitin system has seen previously. And that score in itself is not particularly, well, it's an indicator where you might research. But the nice advantage of Turnitin is that when it does this analysis, it also tells you what the original was that it looked that the student might have plagiarized from. It allows you to put the student's work and the alleged source next to each other, and allow you to judge whether this is really a case of plagiarism. To what extent have they paraphrased, or is it just an obvious thing to be saying in this context? That's been, and the critical thing between the detection of normal plagiarism and detection of ChatGPT plagiarism is that we can do a score, but we don't have, we can't generate the evidence alongside, right? So I think the techniques, the sort of techniques that we need to look for is techniques that generate evidence, and when it's related to software development, then the sort of associated techniques are about invariance and theorem provers and things like that. And when it's about information retrieval, it's about pointing out the sources, making it possible for people to verify the outcomes. There are some generative AI systems, large language models, which do pretend that they're reasoning to some extent. So their reasoning trails are then checkable. They're not always good, and I have some disbelief that what they do is reasoning. I think that they're still reproducing text, but the text they're reproducing in this case is text representing reasoning, and then getting that as wrong as anything else. But who knows? We might get a little bit further with that. But yeah, techniques that sit alongside the AI and look at it critically, verify things, produce confidence levels. I think those are the sort of techniques that we need to work on. So we know that we can establish the value of an AI answer a little bit more than we currently can.
Thanks for that.
Thank you, Colin, for the question.
Okay, thank you. Is there any other person here tonight that I want to say, maybe contribute? Maybe there's something you need to say with regards to the topic of tonight. Okay, it's already 7:45 UK time. Okay, so if there are no other things, once again, just to summarize everything, I know one of the takeaway that's for me tonight is the current AI system that is in place do not support meaningful verifications, accountability, and in a way limiting the reliability in so many critical contexts. And apart from that, I think it's also in many scenarios violates the principles of responsible software engineering in a nutshell. Okay, so I think that is what I would say is the summary of tonight. So thank you very much, Professor Boiten. And also to all of us that are here, I really want to appreciate everybody that have taken their time to be here tonight for this talk. Just to wrap it up, I would say, for those of us that are here, this is at the BCS Leicester branch. We do have a talk like this from time to time. So if you're not yet a member, I would suggest you sign up in order to be a member. So if you don't know how to go about it, please get across to us. So once you are a member, you'll be getting emails from time to time. So when else we are having, because we've lined up events for the rest of the year. You will get email from us, and we give you the topic and the event that is coming up. So in the chat, Professor has already put the link there for you to be okay. That's the short version of this. But if you just go to the BCS Leicester branch, so you'll be able to sign up and be a member of this branch. So once again, thank you very much. John, Glenn, I don't know if you have anything to say before we wrap it up.
No, thank you. Thanks very much, Eerke. It was a very interesting talk.
Oh, thank you. Glenn, I know Glenn, is there anything from you? In the absence of any other thing, once again, Professor, thank you for your time, and
Thanks, everyone.
good night, everyone.